Hello everyone. This lesson is on adversarial machine learning. Adversarial machine learning is basically an attack on the machine learning and mainly on the image classification, in which you can change the input, and the objective is that the model should give some wrong output. Although the model is correct, but you are you're modifying an image in such a way that with minor changes, the changes are not visible to the human eyes. Human eyes still, for example, it's a cat image, human eyes will still see it as a cat image, but the model will not see it as a cat image. Only when this model has been changed. Otherwise, it is okay. I have included some of the libraries here, mainly that we will be using the Torch and Torch Vision, and some of the libraries are PIL to open the image, and then just NumPy and matplotlib to plot something. And currently, I'm using this Torch and Torch Vision, and 1.12 Torch, and 0.13 as the Torch Vision. And this lesson is not a full lesson, but what I have done is, in order to simplify and in order to tell you the core concept behind the adversarial machine learning, I have written some functions, and for that I'll create separate videos. But for this one, we're just using a library called utils, in which I already have functions. So if you're trying to type it, and this may not work without util, but you will see the functions written in the utils in different videos. Okay, so I have included that. So let's say we have an image here, which is I'm just writing it is in a file name. So we have a file name, and the image is stored in a folder called images, and I have a panda image, panda.jpg, and it's true indexes. True index means we are using an ImageNet dataset, and this panda image we know that this is a panda, and its index in the ImageNet classes is 388. This is what we know already. So we expect that model will give us a 388 class, the highest score for the 388 class. So that is the objective of the machine learning, that if it is a panda, then it should give the highest probability for the class, the correct class. But what happens in the adversarial machine learning is, we'll make some changes into this panda, and we'll see whether this model is giving us incorrect class, or still it is giving us the correct class. That we have to see here. Okay, so these are the two things that is our input, that we have a file name and we have the true IDX, and we can create an PIL image from the file name. So this is a PIL image, and we can write pil.image.open, and we can pass the file name here. Okay, so this is a PIL image, and we can display this image. Display the PIL image. Okay, as you can see that this is a panda image, and now we can get the class also from corresponding to true IDX. Okay, so I'll just say print, and since it's an imageNet class, so I have a function here in the utils. So I'll just call this utils.imageNet. So we have a dictionary. In fact, we have a function, and then we have a dictionary. And in the ImageNet, we need to pass just this true IDX, and it will give us the corresponding class corresponding with this true IDX. And we can see this is the giant panda. Okay, so far we know now that this is a giant panda, and ImageNet is also giving this the class. Okay, so now what we are going to do is we are going to pre-process this image. Okay, so pre-process is converting this image to the tensor, and then we want to create a tensor, and then we want to see whether we can still see this panda or not. Okay, so let's say that I want to create image tensor now. So image tensor is equal to, we'll see that in different videos I'll tell how to pre-process, but let's just assuming that we are going to convert to the tensors. Utils dot, and I have written a function called preprocess. So utils dot preprocess, and in this one we'll just pass the file name, file name means that the complete path, that this is the image. So this pre-process will open the image using PIL tensor, and then it will convert in the size of 224 by 224, which are the requirement for the ImageNet, and convert it into a tensor. Okay, so this image tensor we will get it, and then if we want to display this image, let's say I want to see the shape of this image now. So we have an image tensor that has been pre-processed tensor, and we will see what is its shape. And you will see that this is 1, 3, 2, 24, 200. What does it mean is that 224, 224 is the size of this tensor, shape of this tensor. That is the requirement by the ImageNet or the models. Not the ImageNet, but the architecture that we will be using, which is the ResNet. So ResNet needs that image to be shaped by 324, 24. 3 is the name of the color channels, and since we have only one image, so 1 is the batch size. So this is what we are getting in the image tensor. So next, what we want to do is we want to display this image first before we move forward. Okay, so in order to, if you want to display the image, we need to convert it into a numpy array. So if we want to convert into numpy array, so we want to first get rid of the 1. Okay, so that's very easy actually. So we can just write image tensor with subscript with 0. So it will give us 3, 224, 224. Okay, but I have written a function here that helps us to convert to numpy array. Okay, so what we will do is I'll say image numpy is equal to, you just call the utils, and utils dot I have written function tensor to numpy. So just assume that these functions exist, and I'll see different videos in that, and I'll give the links also. Okay, so this is a util, means how to convert a tensor, and the PyTorch tensor, to a numpy, and what we want is that we want to convert this image tensor uh, 0th element. So this will give us a numpy array, and we can use this numpy array to show. And one of the thing is that one modification is that the PyTorch considers the tensors that color, channel, width, and height, but the numpy array considers that it should be width, height, and then the color channel. So we need to transpose and convert. We need to convert to numpy, and then we need to convert it. We need to move the columns like that. So that is all done in tensor to numpy. And next, what we want to do is we can just want to show this image. Plot dot IMShow. Okay, and we can just give this numpy array to this function, and this will display a image here. So we can see that it means that our preprocessor is working fine. So what we've done so far is we pre-processed it, and then we use this image tensor to display the num in the here. So that's what we can see now. Okay, and we can display the title here, that this title. So we can say this plot dot title, and we can get the classifications corresponding to ImageNet from the util, so ImageNet, and we just need to pass the true IDX, and this will give us the giant panda. We can put the semicolon to remove this. So this is the giant panda. Okay, so far it's working fine. Next, what we want to do is we want to now test this image and from the ResNet. So what's the class of this? So far what we know is the true IDX is 388, which is the giant panda. And let's see what ResNet give us. So since we want to use then inference on this image, so first we need to get the model. And model also we can get it from the utils dot get ResNet. So I have written a function called ResNet 50. Okay, so this will give us the model. That's the ResNet 50, and this model will give us pre-trained on the ImageNet. So this model has been pre-trained on ImageNet, and we are getting it from the Torch Vision library. Okay, and I have written a function called inference. So inference will take model as well as the file name, and it will give us the corresponding the predicted class. Okay, and let's say that it gives us the output, and output is a tuple, and I'll tell you what are the elements into that, what are the variables into that. So so far we'll call the utils, and we'll call the inference function from this one. And this inference function will take the model that you want to train. You already have a model. Pass this model that you want to run inference on this model, and then you're passing the file name. That file name is equal to file name, that this is the file name. So this inference will take care of opening this image and pre-processing, and everything will be done in the inference. You just need to pass the file name. Okay, so this is the file name that we want to check, and then this is the true IDX of this file name. Okay, so this is what we know. So once we run this one, so this will be run. So we have something in the output, and that output is not some one value, but it consists of maximum IDX that according to the ResNet, so this IDX is maximum, and this is the maximum probability, and this is the loss, and this is the normalized tensor. So it also gives us that this is the image tensor. We can write it as tensor and normalized, and this is the output. Okay, so this is the triple that we are getting from the ResNet. Okay, so I can print it out. Now let's see that what is the maximum IDX. Okay, so we can see that this is 388. And what's the probability of getting this maximum IDX? Maximum probability. So the ResNet thinks that it is 99.7%. There is a probability that this is a giant panda. So since this is the max IDX, so what we can do is we can use the utils dot ImageNet, and we can pass now, instead of true class, we can pass this now max IDX. Of course, in this case, it's same. So this is the giant panda. Okay. So now what we are going to do is we are going to attack this model now. Okay, so our objective is that we will modify this delta, so modify this image in such a way that when we will display in the Jupyter notebook, human eyes will not see this difference, that what has been changed. But this model can, because model doesn't know that how to visualize this image, it just needs that what are the pixel values in this image. And based on those pixel values, we'll see that we'll see whether it's still the giant panda or not after changing this image. Okay, so but how much this needs to be changed is all this is all in the subject, that adversarial machine learning. First is how to create an adversarial examples, or maybe how to defend the models, so that model shouldn't do the mistake. Okay, so let's take say that we are taking an epsilon here, which is a very small quantity. We can write epsilon is equal to 2 by 255, and we can print it. This is the epsilon. Okay, 0.0078. We'll use this one. Okay, so what we are going to do here is that first is that we have a file name, and we need to pre-process that file name. And once we pre-process that file name, we'll get the image tensor. So we will call this utils dot pre-process. So we have passed this file name here. File name. So we got this one. And then once we get the image tensor, we'll create a delta. So what is a delta? We'll start with 0. So if this image is 224 by 224, we corresponding to this one, we also need a delta. So what we're going to do is we'll add that delta into this image. So that delta will be very small. Okay, so we want that delta to be in the range of this epsilon only. So all of those numbers will be between minus 0.0078 to 0.0078, and we'll add these numbers into these pixel values, and we'll see that whether this giant panda class changes or not. Okay, and you can see that this is a very small number, but still it has a major impact on the models. So models may not give you the right answer. Okay, so in order to create this delta, which is of similar shape of the input, we'll use this torch zeros like. So delta is equal to, we'll call this torch dot zeros like. So initially it is all zeros. So torch zeros like means it will create a tensor of all zeros, but its shape will be like an image. which we have passed. So image tensor. So its shape will be exactly similar to this image tensor. And this delta, this is not a simple delta now, that it's all zeros and we are going to change this randomly. No, we are not going to change it randomly, that how much to change. Rather, we are going to create this using the backpropagation, that what needs to be changed in this delta. Okay, so that's why we're writing it as requires gradient is equal to true. So for this tensor, we need gradient. Gradients will be computed, and then we'll use the backpropagation to update the model parameters here. Okay, so for then how much to be passed is being informed by us by the optimizer. So optimizer will create an optimizer torch dot optim dot sgd. Okay, so Stochastic gradient descent. So you can try with different optimizers also. And in this optimizer, in true training, we don't pass the delta, but we pass the model parameters here. But in this case, we are going to pass this delta. So we have passed the delta in the stochastic gradient descent, and the learning rate, we have kept it very small, as we know, 1e minus 1. Okay, so what happens is when we'll optimize, we'll take the optimizer dot step, so it will compute the gradients and will update this delta. So our objective is to update the delta based on the gradients. Okay, so let's run this one and let's take 30 steps here. So I'm taking that 40 in range 30. 40 in range 30. So what we're going to do is we're calling it as a perturbation. Perturbation is equal to, what is the perturbation? So in the perturbation, what we'll do is we will add this delta to this image tensor. So initially it is all zeros, because this delta is zeros like this image tensor. So that's why we created of this similar shape, so that these can be added. Okay, and then after the addition, we'll normalize this using this our utils library. Okay, so we have utils and we're calling this as normalize, and we are normalizing based on the image tensor plus delta. Okay, so we have added these two tensors, image tensors, and the delta initially 0. So this is initially image tensor only, and we are normalizing. So the normalizing means that the PyTorch, the ResNet or the ImageNet, these architectures also need standard deviation and mean into a particular range. So the normalizing means just modifying the value so that it follows that standard processes of the ResNet architecture. Okay. So we got the perturbation. So our objective is, now we assume that if there is some delta and we have added that noise into the image tensor. So in the further iteration, this will be modified. So we want to we want to predict the class of this perturbed image. Okay, and that is easy for us, that we can compute predicted is equal. So we're not using the inference right now, because we want to update these classes here. And once this part we can compute the final delta, then we'll use the delta to modify this image, and then we'll use the inference. Okay, so the predicted is model, and we're passing the perturbation here. Okay, so perturbation, a perturbed image is passed, and then we'll compute the loss here. And what is the loss? Means then how far is this predicted class from its true class? And true class we know is 388, and it is not going to change, at least for this example. If we use the different example, then definitely it will be different class. Okay, so the loss is equal to the torch dot nn, or maybe just we call nn because we already included nn dot cross entropy loss. And in this cross entropy loss, we are going to pass this predicted, that we have predicted just now, and then also the true IDX. But we need to pass true IDX not, but its corresponding tensor. Okay, so that corresponding tensor can be obtained from the torch dot long tensor, and we can pass this in this one the true idx. Okay, so this is okay. And the improvement here is that instead of loss, it converts the minus loss. Okay, so that is the adversarial attack now. So our objective is not to reduce the loss, but to increase the loss. Okay, so if we take the loss as it is, and if this loss is gradients are computed based on this loss, so this uh, delta will be changed in such a way that the class is improved, but that's not the objective in the attack. So attack is that how to create the delta that increases the chances of model gets wrong here. Okay, so the loss is negative, and then what we are going to do is we're going to just optimize, update the delta. And the normal process in every model is that create this optimizer first, that optimizer dot zero grad, because this is in PyTorch that the gradients are accumulated. So whenever we are going to update the model parameters, or we are going to first back propagation, before back propagation, we have to ensure that the initial gradients or the previous step gradients are zero now. Okay, so initial also we need to ensure that the zero grad. And after that, we are going to use this loss dot backward. So the loss dot backward will compute the gradients, and then optimizer dot step will optimize it. And what is in optimizer? This delta. So what is done is this delta will be updated according to this loss. Okay, so during these changes, so this delta may be, it may possible that delta, the value of the delta, because so far we don't have any control on the delta. Okay, so the delta may be a very large number. And if this delta is a very large number, and when we are going to add this delta in the image tensor, so it may possible that this large number may create a spot here. And then any human eye will detect that there are some changes in this image. This doesn't look like a proper image of the giant panda. So in order to ensure that this delta should be less than some number, so we are going to use the infinity norm, and which says that we're just going to clip this value between minus epsilon to a plus epsilon. Okay, so this is a delta dot data dot clamp, and we're going to pass here that minus epsilon to plus epsilon. Okay, so let's run this code now and see what. And one more thing, that because this is t to 1 to 30, so it's better that we should print some values here. That were how is the loss progressing, whether in magnitude it is increasing or not. Okay, so what we do is, if we can just print after a few steps, we don't want after every step. So if t percentage 5 is equals to 0, so after every 5 steps, we want this to be printed. So print t and then loss dot item. So the dot item is to convert a tensor. If it is a singular tensor only, one element tensor, can be converted to a scalar using dot item. Okay, so this is what it will print. And let's compute. And better is that we should compute. Okay, yeah, let's do it. I think we should print the loss before this one, because after this one the loss dot backward may create a problem. Okay, so let's run this one again. There will be error now, indentation error. Okay, but it's not getting changed. So what happened? Optimizer dot zero get loss dot backward, optimizer dot this one. Yeah, it's not a change here. but why not change here? Clamp and in that cross entropy. Yeah, maybe this the loss our learning rate. Yeah, now it is increasing. Okay, so that was the reason. So we can run it again. Okay, yeah, good. So we can see that loss in the magnitude is getting increased at every step. Okay, so it's okay that that it's getting increased, but let's see what happens now if we add this delta into the image. But is it significant or not significant? Okay, so let's see first that we want what happens if there is no attack. So I'm writing here that there is no attack, and we're trying to use the inference function that we have written. So it will give us some values here, which is maximum IDX, maximum probability. There's a triple here, so we can just write it here out, and we'll just later on divide this tuple into different variables. So out dot inference. So out dot inference, we need to pass this model and file name. File name is equal to file name, and then we also need to pass the true IDX. That's what we have done so far. True IDX is equal to true IDX. Okay, and we'll see that what happens whether it's a giant panda or not from this one. Okay, so this function now return us that what is the maximum IDX and also the maximum probability. This will be the same because we have so far not changed anything. We just want to see the tensor now, that the image returned by this inference function, how does it look like? Okay, so that when we add this delta, then we also want to see. Okay, so this is the origin. This should return us the original image. So max IDX, max probability, and what is the loss, and then the image tensor normalized. So this is what we want, and this is given in the output. Okay, and if you want to predict the label of this one, so label is equal to corresponding to the maximum IDX. So what we want is maximum IDX. So we'll call this utils dot ImageNet and we'll pass this maximum IDX. So we got the label here now. Okay, so we know now what is the maximum IDX, we know what is the maximum probability, and what is the label actually here. So we can just print these three values. These three values are very important for us. Okay, so print these three values and plus the label. Okay, so still is the giant panda, but we want to see whether how does it look like. It should be same, but we just want to see that whether functions are working correctly. Okay, so we have this image tensor normalized returned from this inference. Okay, so what we want to do is we want to reverse normalize or inverse normalize. So corresponding to this image tensor normalized, so normalized means that we know that it has a standard deviation in certain range, and if we want to visualize, then we want to inverse normalization. Then only we can see. So we can create another tensor here, that is the tensor and inverse. Tensor inverse is equal to utils dot, I have written a function there that this is the function for inverse normalize. So you need to pass this tensor here, image tensor normalized, and this will give us the tensor inverse. And the shape will be the same. Print tensor inverse normalized dot shape. Okay, so this is again 132. Now, if we want to visualize, then we don't want this one. So for that one, we can just write the zeroth element. It will be 3, 224. So this is a tensor. Now we can call our function that we want to convert this PyTorch tensor to NumPy so that we can see this image. Okay, so for that we can use this. We can call this not tensor, maybe NumPy. So NumPy tensor is equal to, and we'll call our function utils dot tensor to NumPy. So we have now tensor to NumPy, and we can pass this tensor dot inverse tensor. So we are going to pass this inverse tensor, and this inverse tensor is being converted into NumPy array. And next, what we want to do is we just can show this tensor. Okay, plot dot and show, and we can pass this tensor NumPy, which can be easily displayed by this. So we can see it's a tensor, so, and we can give the label also, because now we know the label, plot dot title, and we can pass this label. Okay, we can just suppress this one with text, just giant panda. And if we want to show the probabilities, that what's the probability, we can just write it that this is a label, and we can pass. In fact, this also needs to be like this one. So this is a label, and in this one we can pass the maximum probability. And you can see it's 99.7% probability of giant panda, which is good, which is actually it is a giant panda. So we want this to be a high probability. So what we are going to do is, so we have seen this is a no attack, and now what I'm going to write in this, the whole code in a very compressed format. So we don't need this one. Maybe if we want this one, then it should be the last element here. So here what I have done is we have got the label here, and then we have inverse normalized. I'm writing it in one cell so that it's easy to change. Okay, just copy, and then everything will be in one cell. Okay, so this is the giant panda now. So we don't need one to display this shape of the tensor. So maybe now we can comment it. So maybe we can comment this one also. Okay, so great. This is the output from this cell, which has no attack, means we still have not used the delta. Okay, so now let's do the magic now. So what we're going to do is attacking model. Attacking. So everything is same. The only thing that I'm going to change is delta is equal to delta. Just that I'm going to pass this delta. Okay, just run it. And comma required, so just pass the comma. And now you can see it's saying Italian Greyhound, and that is also with 99.4% probability. This is a high probability, but it's nowhere close to the Greyhound, Italian Greyhound. Okay, so this is what it happens. And if you want to see this delta, then what is the delta actually? And the human eyes can't detect, there is no change that is visible change to us that we can see. So something has gone wrong by adding this delta. Just passing this delta, so internally in the inference function, so this delta is added to this file, is opened and pre-processed with, it's the same function here. So this image is added to, not here, but here. Yeah, image tensor plus the delta is added, and then we check what's the predicted class here. Okay, so let's see that what is the delta now. And we can, I have written a function here to display the delta. And this delta is 50 times known, because by default delta is nothing, it's all black, it's all very small number, you can't see it. But once we zoom this delta and by 50 times, so we'll see that this is the delta. So this delta, which is 50 times zoomed, is being added to the original image, and the original image is now of Italian Greyhound. So that's the definition of the adversarial attacks. So not only that, this one, that this is a problem in that it will give some random class. So that is not the question here. But what is happening is that you can make this model to predict a wrong class with high probability and your own defined predicted class. Think of a facial recognition system which which allows a person to go into some confidential area based on a face recognition system based on the face of a person. So now if the person can change a face in such a way, it's not that it is predicted some other person, but a targeted person, maybe a very important person of that company, okay, or that area. So this may be a serious breach of trust or confidentiality matters here. So in case that happens, and we can see that in this example that can happen. And so what we're going to do here is that so far this is the Italian Greyhound is the 99% for probability. So what we want here is that instead of true class and some random class, we want a target idea. So our objective is very much clear now, that we want a model to give this target IDX 404. Okay, so we want model to predict 404 class. Now this may be looks like, and how is this possible, but actually it is easy. And in order to prove this one, so what we need to make a changes here is in this code. So I'll just copy this code. Basically we want to create a new delta here. So this delta will try to make a prediction to 404. And how is this possible? So we have this loss we have computed. So far what we have done is the loss has been computed with true IDX. Okay, so this is the loss. So objective is that loss should increase in this direction, but at the same time, we can make another change here, that this loss, we are saying add this loss. So this is saying reduce this, increase this loss, and this function will say reduce this loss. Instead of true IDX, we are saying that target IDS. That's the only change that we need to do. So what's happening in this code is, so at one point we are saying the increase loss with respect to the true, but reduce loss with respect to the target. Okay, so what will happen in the training is that your deltas will be optimized according to this concept. Okay, so let's run this one. So we have computed the delta here. So maybe loss is not that high here, but let's see whether it's give us our targeted class or not, 404. And now I'm going to use this code, attacking. It's same code. I'm not going to change anything here because the delta is already been computed, and this delta will be used here. And again, this is not a no attack, but attacking. Okay. So we can see that this is an airliner, and if you print it here, whether this is 404, yeah, it is correct, 404, which is the airliner, and it has a very high probability, which is 80%. So model thinks that 80% chances is airliner, and we can see that this image that has been used by the ResNet has no visible change in this that human eyes can detect. So this is the real threat to the machine learning, but there are some solutions into that, and we'll see some different videos in that, and I'll also cover the utils library that I have created, in which there are some help function to convert to NumPy and to display, and mainly the inference function. Because inference is the engine of this one. So I'll explain in a different video. I hope you liked it. Thank you.